Welcome to the ORS virtual scientific session, Can Computer Science Help Us Understand Biological Systems? Organized by Jasmine Sambalian. Dr. Sambalian is a research fellow in osteoarthritis at the University of Brighton. Her expertise lies in utilizing cellular, molecular, and in vivo approaches to study musculoskeletal aging. Dr. Sambalian began her career pursuing a PhD with Professors Tim Skerry and John Mathers at the MRC versus Arthritis Center for Integrated Research into Musculoskeletal Aging at the University of Sheffield, with focus on interactions of hormonal and mechanical stimuli on the skeleton, a subject with relevance and potential impact on bone pathologies, including osteoporosis. Last year, Dr. Sambalian received a new investigator award from the Bone Research Society and the British Orthopedic Research Society. And with that, I'm happy to introduce Dr. Jasmine Sambalian.
Thank you very much to Orthopedic Research Society for making this event possible. It is my pleasure to introduce and welcome today Dr. Hector Zanel. Dr. Zanel has more than 20 years of experience in academia and industry in 5 countries. As a member of the payload team at Massachusetts Institute of Technology, he has designed and wrote tracking software for NASA for the Mars Gravity biosatellite conceived to test the health and behavioral effects of artificial microgravity on orbiting mammals. He was a research fellow at Wolfram Research, where he helped develop the factual artificial intelligence answering engine behind Apple's Siri. He has published more than 100 papers on symbolic artificial intelligence as a senior researcher at University of Oxford Computer Science Department and as a lab leader of the Algorithmic Dynamics Lab at the Center for Molecular Medicine of the Karolinska Institute. Dr. Zanel is also director of Oxford Immune Algorithmics and Oxford University spin-out. Before we begin, let me remind the audience that we will have questions and answers session following the presentation. Please submit your questions at any time during the presentation using the chat button on the bottom of your screen. I would encourage you to input questions as and when you think of them. This would be addressed in Q&A session at the end. It is my great pleasure to welcome Dr. Zanel, and I would like to hand over to him to begin his presentation.
Thank you very much, Jasmine. So let me start by thanking Dr. Sambalian and the Orthopedic Research Society for the invitation. And now let me share my screen. I hope I have permission to do it. Yes, I have. There you go. So today we are going to be talking about what type of artificial intelligence is needed for what type of medicine and healthcare. And I have no conflicts to disclose other than the ones we have already said. So I am affiliated to Oxford Immune Algorithmics and Karolinska Institute. And you may have heard a lot of AI in the recent years. There's a lot of hype and a lot of news regarding the use of AI in many applications. But what's something I like to do always is actually to understand the challenges and limitations of something to be able to actually understand better that something. In this case, instead of adding to the hype of AI, I would like to address some of the challenges and limitations of the field. And here on the screen, we have 4 of them. So one of them is scalability. So unlike humans that require only a few experiences to be able to abstract and then generalize, machine learning and deep learning, as you have heard, for example, neural networks, require a lot of data. And that data actually has to be annotated. And for example, for self-driving cars, you have to show an AI thousands of cars crashing into things for the AI to actually understand that crashing is not a good idea when driving a car. And for most humans, actually, there are humans that have never crashed before and perhaps never have seen a crash before. And they understand that it is something that they shouldn't be doing, or that they have to avoid. So there are profound differences on how we learn things, and scalability is one of them. The other one is understandability. So machine learning and deep learning deal very poorly with things like reasoning, modeling, inference, abstraction that has to do with what I was talking about, right? So anything related to cause and effect, to understanding a chain of cause and effect. Then there's also the problem of explainability. So neither the model itself or even the experimenter, if you open what is considered to be a black box, a neural network, for example, there's nothing to understand inside. There's just a set of real value numbers that doesn't tell anything, and there's no correspondence with anything physical, so there's no state-to-state correspondence. And then there's a problem of bias that has been in the news for some time now, like a few last months. And humans tend to introduce their own bias, but also machines can introduce their own bias by themselves without humans noticing it. And there are many examples, and actually, let me start with some of them. So very recently, I think last week, I don't know if you saw this news, but the MIT apologized for a very large data set that is called ImageNet for labels that associate some images of people with bad words. I don't know, for example, a child molester. And when you look at the picture, it is just a man or a woman that has nothing to do with, or there's no way actually to infer whether it is a child molester or not. And that is very bad, right? Because if you are using that as a training set, then your neural network is going to be biased to actually associate those labels to people that is trying to classify. So actually what the MIT decided was just to take down the whole database. And you can see how problematic that can be. And they didn't realize this before, because we are talking about a very large database that no human has been able to actually go through. There's another one, and this is kind of a combination of human and machine bias, where you have two people that either committed exactly the same offenses, or even you have the white person committing more offenses, and then you have a color person with less offenses, and the risk associated to black people or brown people is much higher than white people, even when starting from either exactly the same offenses, or as I said, the opposite, the white person committing more offenses. And this has been published before, and this actually happens all the time, and not only with machines, but with humans as well. So what we are doing is basically transferring what we are already doing among humans to machines, and that is one aspect of high concern. Then we have another kind of bias. For example, when we go to the GP or the physician, and we are ill, the first thing that they do is actually to compare people with population reference values. And that is some sort of a bias, because there's enough literature, for example, in blood testing, indicating that people have very different values, and they shouldn't be just compared to population reference values. And that is a form of bias. And there's no machines involved, and we do this all the time. So one of the things, for example, that we have done is to introduce something that we call the immune score. We have a preprint released a few months ago that tries to learn patient baselines for blood testing. So basically the score adapts to the values of a person over time. And instead of having to compare their results, blood test results, against population reference values, it compares it to personal reference values, and then you can determine change, which is indicative, potentially indicative of a condition or disease. And this is actually how it looks like. So when you have some data points, in this case, these are lot testing analytes, and you have the population reference values, then people start shifting to one side. And what you can do is actually to adapt the values over time to try to infer the new normal for that patient. So this is something we are trying to do at the Oxford spin-out with an app that is oriented for clinicians and medical professionals. And with this type of risk assessment score, what we do is actually to triage patients by how much they require attention, for example. And you can do all sorts of tests to see if actually the immune score is actually working fine. And what we did, for example, was to test the score against 100,000 cases, blood test results, where we anonymized all the data from that cohort. So there's no race or gender involved. But obviously, you always have to find the right balance, because you also know that, for example, gender can shift some values in the case, for example, of full blood counts. There's difference between males and females. So it is always about finding the right balance, and there's no recipe for being completely unbiased. So this is an ongoing thing that someone has to look after all the time. So something that we're trying to do is to help transform medicine from symptom pattern matching to causation, and we call that causal diagnostics. And you can see that I didn't choose the example by chance. So this is again the self-driving case, where you don't want Tesla or Google, for example, training cars on using something that doesn't understand cause and effect and requires a lot of very specific examples to understand that it shouldn't be hitting people. And medicine in some way either has been operating on that assumption or we are making it that way by introducing the kind of wrong machine learning into medicine. Because the current machine learning, as I've been saying, and we are going to be exploring in the next slides, is not able to understand this concept. And by the end of the talk, my hope is that at least we pencil some of the directions in which we could walk through to try to come up with ideas on how to introduce these fundamental concepts into artificial intelligence if we want to apply AI to medicine and healthcare. So this is very interesting, right? Because we have heard so much about AI, and the question is, where is AI in the pandemic, for example? Shouldn't it be telling us what to do? And it is completely absent. And that is not because people haven't tried. So actually, researchers from the University of Washington tried to come up with a model, but it has failed. And most models actually haven't done much better. And one of the reasons is because conditions rapidly change all the time. So one way to see this is that we have a virus that is getting into several countries, and those countries react in different ways. And depending on how they react, the outcome changes dramatically. And none of these models have been actually useful. But this is a very good example of how current AI is not coping very well with interventions, which is very much cause and effect. No? So you intervene onto something, and you may have a different outcome. And when AI that is only trained on pattern matching is very bad at adapting to those conditions. And actually, AI has been used in the wrong way when it comes to COVID-19. So there was a company, Sphere, that published some results and even had a model. But when you test the model, it turns out to be incredibly simple. So what the model or the tool does is to divide by 20 to predict mortality. So basically, you provide the age of a person, and it gives you a percentage of risk of death. but it is completely linear, and we already know that it is not linear at all since the beginning of the disease. And then when they were asked, they pretty much answered, oh, this is what the machine learning algorithms came up with. So instead of using it in a positive way, was a way to actually kind of obfuscate what was going on behind. And that is exactly the wrong way of using ML. We should be owning of what we are doing and understanding what is going on. So how did it come that we managed to kind of dumb computers down, right? Because what I'm saying is basically that AI is not even able to do things like adding two numbers, like 40 plus 2. If you don't present all possible cases of addition to the a machine in the first case. So basically you have to have a training set that is huge, that shows all possible arithmetic operations for the machine to actually be able to do the operation. And that is very strange because actually the original strength of computers was like a calculator. So actually in some countries, the name for a computer is a calculator. So there is something missing, right? That's the message, because something that we could do with something much simpler, now we are supposed to have something much more intelligent, but it is not able to do even simple things that before we could do with some other technology. So this is already suggesting some sort of solution, right? Because what I'm going to suggest at the end is, and you're going to see how, is that we can combine the strengths of the two things together. So let me explain a little bit more about what is the difference between these two worlds, no? Because basically what we are talking about is that we have two worlds, one of the symbolic computation that is able to do arithmetic operations, inference, logic, and another one that looks very organic, which is the neural networks. And unfortunately, organic is not is not a positive adjective in this case, because it does very well for some things, but it's very fragile, and it is not able to do some other very important things. But this all comes down to what is possible with statistics and data-driven approaches as compared to model-driven approaches. And this is a classic example. So you may have noticed, for example, that cars on a road kind of come in batches. So you always see like spaces in between, large spaces, and then suddenly 10 cars come all together. And actually, this is very well known when in textbooks to explain one kind of distribution that is called Poisson distribution, which is this one. And what this tells us when it is related to time or space between cars is basically that most of them, actually kind of almost 50% of them, when they come together, they come very close. Like this is seconds. So between 2 and 3 seconds, most of the cars are distributed in this way. Obviously, they cannot come all at 0 seconds. This is probably just a microsecond, because they will be occupying the same space. But when they come together, they always come in batches. But this is not telling us the full story. So there's no cause or first principles, or it's not a mechanistic explanation. We still remain puzzled on why is this. And some of you may imagine why this is the case. So one way to say it is some cars are actually slower than others, and what happens is that slow car actually is holding back the other ones in the back. So that's why we see batches. But you see that the interpretation of the statistics came out of the model. So there's nothing in the statistics actually telling us that that's the cause for this phenomenon. And that is the main difference between being descriptive or being mechanistic. Because the mechanism would be able to reproduce the distribution, but the distribution itself doesn't tell you what is the cause for the phenomenon to be happening. This is another example of what may happen with statistics and correlation. So these are data points on a plane, and basically all the statistics are exactly the same for the correlation of points on X and Y. So the Pearson is almost the same as Spearman, and actually the way to do this is with a method that is called annealing, which is kind of moving every point very slightly, like in Brownian motion, to keep all the statistics the same. But suddenly you change completely the shape, right? And for us, these two shapes mean something completely different that the statistics is completely missing, because we have exactly the same values, but for two completely different objects. And this is what is happening all the time with AI that is based exclusively on data-driven approaches and statistics. Here is another one very interesting. So all these plots actually have also the same statistics, but they have completely different shapes. So if you take the correlation between X and Y, basically you get all the same statistics. And unfortunately, that is what is going on behind current AI, because they don't use anything much more sophisticated than this. So in neural networks, what is behind is something that is called a cost function, which is some sort of function that is trying to approximate the alleged ground truth. And that function is basically a correlation function between what the neural network is seeing and the internal model. And by internal model, I mean just the architecture of the neural network, because as I said, there's no real model in the sense that there's nothing that you can actually run step by step or has a state, an internal state. So this is the fun part of the talk, because I'm going to show you how modern AI epically fails at very simple things. So this is a bot that receives images and tries to predict what is on the image. And it was developed by Microsoft, and these are examples from 2017, but I'm going to show also examples from this year, from a few months ago. So in this case, the image that was given was this one, and the AI predicted that was a cornfield, which perhaps is not completely silly, because if you're kind of far away, it almost looks like a cornfield, perhaps. This one, according to the AI, was blue shoes. It doesn't look anything like shoes to me. And this one is even more puzzling, because it says that it's an airplane. Perhaps it believed that it was a blueprint or something like that. More troubling are these ones, because these ones are even classified correctly by another type of neural network. All these are kind of gold standard neural networks, or vanilla based neural networks. And what you have is that you flip a single bit, and then the neural network gets completely confused, and instead of getting it right, for example, in this one was a bird, and then you flip this bit, and with almost 90% certainty, the neural network now says that it is a frog. And in this one as well, so at the beginning it got it right, it is a dog, but then you flip this single bit, and it says with almost 76% confidence that it is a cat, and so on. So this basically tells you that even when you get it right at the beginning, and you see all these news about AI got 100% accuracy at classifying cancer tumors, for example, then if you perform a single change to some of these images, or most of them, you can find the exact pixel where you actually have to make the change. It will probably get it completely wrong. And there has been some ideas on how to try to fix this. So for example, there's GANs, that stands for Generative Adversarial Networks, that try to come up with fake images based on the real ones. So basically this will be, for example, a fake one, right? That if you flip only a bit, and then you train your neural network again to accept that as a dog still. And that has some advantages, but it is not actually solving the very first problem in the first place, which is that the neural network is not understanding what the concept of a dog or a bird. Otherwise, you wouldn't be able to do this, just to flip a bit and then get it completely wrong. And you may think, oh, this was in 2017, maybe today is completely different, but it is not. So this is 2020, and this is a very recent paper. And again, it is exactly the same. And you can see that now perhaps the resolution is much better, because perhaps this was 3 years ago, and it took a long time to train the network. I don't think that is the reason, but let's assume it is. This one is much higher resolution, and again, you have exactly the same kind of thing. So you get it right the first time. This is a painting, and then you move something, and it says that it's a goldfish with almost 100% confidence. Or a highway, and then you move something, and it is a dam, and so on. So this is today. So not much has changed in the last 5 years. And there are more sophisticated examples. You can think of this as attacks, because basically what you're trying to do is to fool the neural network, and that's called an attack. So in this case, for example, the neural network get it right. It is a school bus with a 100% confidence. But if you move it slightly, then you start getting all sorts of strange objects. And that's only because you change the angle of the object itself. And we have several examples here. And then an equivalent one is just to move the angle of the camera instead of the object itself. And then again, you have the same problems, where if you had a neural network actually understood or had the concept of what this picture actually means, then it wouldn't matter much if you just change slightly the angle. Another interesting one is when you have all the objects separately classified correctly, but then you put them together on top of each other, and then the neural network gets completely confused and again starts doing all sorts of strange things. Again, exactly for the same reasons. Here's another one where you have some images at the beginning, and then you combine them with some noise. And for us, it looks exactly the same. But then for the neural network, all these three images were school buses. So at the beginning, the neural network got it right. You add a little bit of noise, and then the neural network thinks that all these three images are school buses. Here another one, so a panda, then you add some noise, and it says that it's a gibbon with almost 100% confidence, even greater than when it was saying that it was a panda. And this is one of my favorite ones because it tells you what the neural network is actually doing. And it turns out that if you train a neural network, for example, to classify cats and dogs, most of the time what the neural network is going to be picking up are features that are not related to cats and dogs. So it turns out that this neural network was classifying at almost 100% accuracy, because most pictures of cats comes from indoors and dogs are outdoors. So the neural network was actually picking up the grass color. And it was actually very difficult to find out because, if you open the neural network, which is kind of sort of a black box, you only see numbers. There's nothing telling you, oh, actually, we were picking up the grass. So it is not very interesting because you can see what is the problem. If you have now a cat outdoors, it's going to classify it as a dog. So it was not picking up the right features. And there are even more sophisticated things that have been proposed even this year, where they do some sort of what they claim is a symbolic regression, but it is mostly about connecting equations to data that those same equations were producing. And it has also same type of problems because, again, you don't know what the neural network is actually doing, and it may be picking up the wrong features. So what are the ideas of actually try to solve some of these things? And Judea Pearl, for example, who is considered to be one of the founding fathers of AI and has come up and has worked on Bayesian networks for many years, has been advocating for trying to teach neural networks the concept of cause and effect. And that has a lot of implications because it means that you actually come up with some sort of AI that is able to perform inference. And actually, we were pretty good at doing that. And that is called a strong AI. So with things like expert systems, for example, or theorem provers, that's exactly what they do. So they come up with very large chains of cause and effect, for example, to prove a theorem from a set of axioms. But soft AI, which is the place in which areas like deep learning belong to, come from the opposite side. So instead of dealing with symbols and chains of cause and effect. They are more like organic in the sense that they are able to classify things with high accuracy, even if perhaps not very robust as we have seen. And our own idea is basically to try to combine these two things. So this is actually how we think we can fix it. So to put both things together. And this is what we have been doing in the last few years. And actually this year, the term Neurosymbolic AI has been proposed. I think it has been already around, but it is getting traction. And you are going to be hearing it more and more. But we have been working on this for a few years, and that's precisely what we do. So to use symbolic computation and Bayesian approaches to try to come up with very intelligent algorithms that first require way less training sets, so they can be much smaller. And they are able to deal with things like cause and effect, even if in a very basic way, because it requires a lot of computation. But this is a set of papers that I would highly recommend you if you're interested in this area. So this came out last year. And in some of these, for example, we are showing how we can help with the challenge of nucleosome occupancy in DNA sequences, which is perhaps the second most important challenge in molecular biology, only after protein folding, because it has to do with genetic regulation. And we show how our measures actually can help with to come up with training-free approaches to this problem. And Nature actually produced a very nice video explaining what we call the causal deconvolution. So I would highly recommend this video because they highlighted the research that we have been doing the last few years. And this is another interesting quotation from Sidney Brenner, who was awarded the Nobel Prize in Medicine or Physiology from Karolinska Institute. And he wrote a small piece in Nature that is called Turing Centenary Lives Code Script, where he was actually saying that symbolic computation and the work of Alan Turing was key to understanding biology. And he was highly criticized. It is probably a controversial piece of work, but I think he has some very good points. And again, this is what we are trying to do and combine symbolic computation. So this is a representation of a Turing machine. For those that don't know what is a Turing machine, it's some sort of general purpose computer. And the idea is that it is a reprogrammable computer. So by giving it an input, you can make that computer to behave in different ways, which is basically exactly what we do with computers. So computers are some sort of specific case of a Turing machine. And then on the other side, we have all these statistical approaches, which in this case, for example, is representing a neural network, which is heavily based on statistics. And both worlds have their strengths and limitations. For example, on this side, it is very difficult to deal with noise, although there are some ways to do it. But this one is way better to actually deal with noise, for example. So it makes a lot of sense to actually try to put these things together. So there's only a couple of slides that I would like to show you with a little bit more meat, but then don't get worried, it is going to be very short. So there is a fundamental concept that is called Kolmogorov Chaitin complexity, and that was developed in the 60s. And this is actually a way to deal with the limitations of statistics, and in particular correlation, versus what we would like to do, which is causation. So we have two sequences, for example, here. One is called the 2-more sequence, which you can build very easily. You start with a 0, and then the negation, the binary negation of 0, which is 1. Then you take, again, the full string and you negate it, and it is 1, 0. Basically, you take the first 2, you negate, and then you concatenate. Then you have 4 bits, and then again, you negate them, and then you build the next 4 digits. Right? So it is very easy to construct this string, and I just gave you the algorithm to do so. So keep this sequence in mind. Then we have, for example, a segment of pi in binary. So as you may know, pi, the mathematical constant pi, can be built with dozens of formulas, because it basically is a relationship between two mathematical objects, usually related to the circle, for example. But it turns out that actually these two sequences have been proven to be what is called Borel normal. And actually for pi it is not known, but it is believed strongly to be Borel normal, which means basically that these sequences look random for all purposes. And actually you can see it on your screen, they don't show any irregularities. And even when the sequences themselves don't show any irregularities, we know that these sequences are not random because they were generated by an algorithm that I just gave you. And for pi, there are many formulas to provide it. So we would like to tell something interesting about these sequences instead of just saying, oh, these sequences are like any other random sequence, because actually they are not. So the idea was to come up with this definition of complexity, which is based on a computer program. So the idea is that if your string is S, so it could be any of these two, what you try to find is a computer program P that runs on a general purpose computer, but then you try to find the shortest of those computer programs. But even if you are not looking for the shortest, even having just a computer program, then that will be a causal description, a generator for that string, especially if it is shorter than the string is itself, because the kind of things that you avoid by having the shortest program is that you don't want a program that just tells, for example, print S, because that is a silly program. It is just reproducing S by using S itself. So in science, what we try to do is to shorten the theory. So the theory usually is much shorter than the phenomenon that you want to explain. Otherwise, it is kind of useless. And you can see the power of this definition, because it is exactly what we want when we are dealing with causation. So what we are trying to do is to come up with some sort of model that we can run on something to reproduce the observation. So what we did was actually to take this definition and try to apply it to these problems of causation. And this is not any definition, by the way, and this is why we put here this comment, because this is the mathematical definition of randomness. So you may have heard many definitions of randomness. You may have an idea of what randomness is, but actually there's an agreed definition of randomness in mathematics, and it's this one. And that is because actually mathematicians in the 60s tried to come up with many definitions of randomness, and at some point they were able to mathematically prove that all of them were equivalent between each other. So that basically means that this is very fundamental. This is the definition of randomness, so it is not just any random measure. So what we did was to use this concept to come up with some way to automatically generate models of the world or from one observation. So let's say we have these two strings. As you can see, this is the sequence of natural numbers, and this is also the sequence of natural numbers but in binary. And let's say that you are using some sort of statistical method to try to characterize these things. You wouldn't see anything because these two strings would look random for any statistical model. I mean, unless you actually do some sort of mathematical messaging, there's no way to find any patterns in these sequences. So in other words, statistics wouldn't tell you anything interesting about these sequences. But if you use our methods, what we do is actually to run some sort of general purpose computer program that tries to find computable models for these observations. And one model, for example, is represented here, and it is a binary counter, it is called. And it turns out that that one, so by the way of which we approach the problem, when we find one of these models, we actually have a state diagram. So this is definitely a generative model that is able to run and has a correspondence with the observation. So you can follow this model step by step and actually see if it corresponds to your observation. So it is a completely different world between those two cases. On this one, you don't have a model. you are trying to do a descriptive characterization of your object, but because it has no statistical patterns, as most of the objects in nature, then you would completely miss the point that these sequences have anything interesting. And you can see how interesting they are. And these are only two examples, but actually mathematically you can prove that most of the strings are actually of this type. So they don't show any statistical pattern, but they are algorithmically simple. So they are generated by a model, a shorter model. And on the other hand, you have a set of models, because what we do is not only come up with a single one, but actually a full set of models that is able to explain the data. And then you can do all sorts of experiments to see if your model actually corresponds to the data. And one of them is actually to do interventions and perturbations. So we are going to get there very soon. But this is a beautiful concept that I would like to explain briefly. So it is a connection between basically traditional probability and statistics and what is called algorithmic probability. So the kind of complexity I was talking about related to computer programs. So let me explain it. Imagine that you wanted by chance produce the digits of the mathematical constant pi. Forget about the 3. So you want by chance, by typing on a typewriter, to get these digits right. So if you wanted to get the first one right, you have 10 options. So it is 1/10 chance that actually you get it right. If you wanted to get also the 4 right, then it will be like 1/100, right? Because now you have 100 of these possible guys and only one is the right one, which is 1 and 4, and so on. So actually the probability to get this whole thing right vanishes exponentially. So in other words, it is incredibly difficult to produce pi by chance by typing on a typewriter. And this has to do with this funny infinite monkey theorem that you may have heard that Emil Borel came up with. And the idea is that if you have a monkey typing randomly on the typewriter, if you wait long enough, it would produce the works of Shakespeare. But if you do the actual math, it would take longer than the age of the universe. So how come that actually we have monkeys? Well, the answer is that we don't type by chance. There are laws of physics. And one way to simulate this is actually by replacing the typewriter by a computer. And then the question is different. The question is, what is the probability of producing the digits of pi by typing a computer program on a computer? And then things change dramatically, because you don't have to type digit by digit. What you have to type is actually a formula that produces pi. But because pi is of low algorithmic complexity, as we saw before, right? Because it can be generated by many mathematical formulas, then you only have to get one of those formulas right, and you would have for free the infinite number of digits in pi. So that is a beautiful concept, and it is called algorithmic probability, and this is the formulation. And actually it is related to the other definition I gave of algorithmic complexity, and it is equally fundamental. It is so fundamental that it's actually called also the universal distribution. And one way to see it is basically that you are combining the power of computer programs, the work of Turing, with the power of Bayesian statistics. So you can update your prior by taking into consideration the complexity of the object that you want to produce. And this is exactly how we produce our models and how we choose our models. So basically we favor those smaller ones. And actually one way to see this definition is as a characterization of Occam's razor. So as you may remember, Occam's razor favors simplest explanations. And in this case, it is a formalization of simple in terms of length, computer program length. So the shortest computer programs are the most likely to be the true. But that doesn't need to be the case. Actually, we produce all the computer programs that are able to produce or to explain the observation. And then you can analyze the spectrum of those computer programs in any or according to any other criteria, including, for example, whether it is biologically relevant. So over the course of history, we have been doing to some extent something like this, and there's some sort of a spectrum that you can see where some things are completely data driven. So for example, regression, correlation, and current machine learning. And some other things are actually more model based, like Boolean models, Bayesian networks, uh, Markov chains, deep learning. So this is a kind of a neural network that is more on this side because it uses Markov chains. But for example, when we try to model natural phenomena as a differential equation, we are creating a model for that phenomenon. And algorithmic probability basically is a way to rule them all, because a differential equation is also a computer program that you can run on a general purpose computer. So in some way, algorithmic probability is very fundamental, and it is basically the way in which you can produce models and discover causality. And that's why we call it small data matters, because we are so interested in big data, but actually because it is the scientist that comes up with the model, which is a small data part, but it is fundamental. So this is how fundamental it is. Some of you may recognize who this person is. This is Marvin Minsky. He passed away a few years ago, but he's also considered some of the founders of AI. And he made this astonishing comment a few months actually, or a couple of years perhaps, before passing away. So he said, "It seems to me that the most important discovery since Gödel was the discovery by Chaitin, Solomonov, and Kolmogorov of the concept of algorithmic probability, which is a fundamental new theory of how to make predictions given a collection of experiences. Everybody should learn all about that and spend the rest of their lives working on it." So this was astonishing for me, because it's basically the description of my own life. Now, this is what I've been spending most of my time trying to understand algorithmic probability and apply it to many domains. And it is astonishing as well, because he never really had the chance to work on this field. So he worked on many other things. And then by the end of his life, basically, he's kind of acknowledging that this was a very important area that perhaps he would have liked to study and contribute to. So this is a graphical explanation of how we do it. So what we do is, let's say we have a phenomenon behind. So this is a Rube Goldberg machine, which is kind of a whimsical machine, because it does all sort of silly things, and you may have seen this in ads and those kind of things. But it is a nice way to illustrate how our algorithm works. So what we do is to look at small batches of information that may tell us whether there was some cause and effect interaction. And actually, our algorithm doesn't look like this, but looks more like this, because we traverse the whole phenomenon. And by phenomenon, I mean the data that is producing that phenomenon. And then you traverse all the thing looking for what we call causal patches. So small pieces of data that you can explain with a small model. And then the combination of this, or the sequence of all these small models, basically give you a large model that can tell you something about the original phenomenon. So we have done all sorts of things. And for example, there has been some applications to cognition. And this was a paper that we published a few years ago, where we were able to reproduce some of the that are well-known lifetime cognition curves, where you see people's cognitive capabilities increasing early in time and peaking perhaps around 25, then with a small decline afterwards, and then by 65 or 70 years old, then there's a greater decline. What is interesting is that we did all this by only applying 5 tests that then we run through our algorithms. So these tests involved asking people to come up with sequences as if they were produced in nature or by chance. So we asked people, for example, imagine that you were tossing a coin, so produce a sequence of heads and tails as if they were random. And then let's say that you draw a card from a deck and put them in some random order. The same for dice and dots distributed on a space, and then also a configuration with black and white squares. Interesting, but this was with more than 3,500 people, ranging from 7 years old to 80. And we were controlling for everything, education, language, gender, beliefs, and so on. And nothing was indicative but age. And the 5 tests gave almost exactly the same results, which was so interesting that actually a lot of media, including tabloids, picked it up. There were like publications in like 40 countries about this, which I think it is over the top, but anyway, was an interesting research to do, and something definitely you should look at if you're interested in cognition. And then we apply these same ideas to other cases, including fruit flies, redwood ants, rodents, and humans, all the time trying to characterize behavior and see whether our models would tell anything interesting or already known, but without using information from the literature. So basically replicating what others have been done with much more resources. So see, these are some of the other papers, but now there are even more than I know of, because people are using this for many other things in cognition and in some others, but I think cognition is one of the main applications. So let me briefly, just to finish, explain what is next and why I think this deals well with perturbations and interventions, because you may remember that at the beginning we were saying that AI is not giving us any good explanations for COVID-19 or predictions for COVID-19 development, because they don't deal very well with interventions. So using our own models, we came up with what we call algorithmic information dynamics. And the idea is, again, you have some piece of data. By the way, by piece of data can be anything. Just for simplification, we tend to use strings, but it can be anything. And let's say you have a piece of data and then you introduce a perturbation. And what algorithmic information dynamics is all about is to look at what happens in what we call the model space, or it could be the software or model space. So basically what happens to the models that you had before explaining that piece of data when you perform a perturbation. So let's say you perturb this bit, then if you had this explanation, that is very simple, right? Because it is basically just an iteration producing any number of ones. But if you introduce that perturbation, basically you perturb also your models behind, because there's no way to produce this piece of data with this piece of computer program. So you have to introduce now a new line of code to explain perturbations in the middle of the sequence. And basically this is telling you that if you increase the size of your models, then it means that not only there was a perturbation, but it was a perturbation that looks random for the purposes of comparing between these two cases. But then you have all sorts of interesting cases. Let's say that you actually have something that looks random, and then you apply also a random perturbation. Then what you have is that there's no changes in the computer program behind, because the same 2 digits that you modified need to still to be accounted for with the same kind of a computer program. So this is the silly program print the same object, because if this is random, then there's no way to compress it into a shorter computer program. So basically this is a way to not only tell that there was a random perturbation, but also that the original data was random itself. And then you can translate this into more interesting objects, including networks, for example. And in one of the papers I showed you before in one of the journals, iScience, we showed how to deal with genetic regulatory networks and how perturbations, which can be translated into knocking out a gene, for example, how you can create models characterizing those changes in your genetic regulatory network. And this is exactly the same case, and you have all sort of all type of behaviors by having these networks. And this kind of algorithms can be used in all sort of machine intelligence tasks like model generation, hypothesis testing, feature selection, and data dimension reduction, for example. We have an online algorithmic complexity calculator in case you want to test some of these things. And it includes all the data, for example, for the cognition experiment. So you can play with the original data, for example. And I'm going to stop there, and I will be happy to answer any questions.
Lovely. Thank you very much, Hector. Thank you, everyone, for your questions as well. We only have a couple of minutes left. There were a couple of questions. The first one was, could artificial intelligence be a good tool for identifying patterns of infection? So, for example, if public health organizations' data were assembled quickly, do you think AI might be able to assist with finding natural history of epidemic more quickly, analyze data from earlier outbreaks, which might be of interest of prediction, and plan faster, more focused response for future prevention efforts?
Yeah, that was the hope with current AI, but it hasn't been very useful as we saw at the beginning. But and we are hoping that with these new algorithms, we can do better than that.
Okay, lovely, thank you. Another question is related to your recent publication on developing novel method and algorithm for improving the quality of images obtained from human microcomputed tomography. Obviously, I use microCT widely in my lab as an imaging tool to study osteoarthritis on model organisms. Can you tell us how applicable would that method be for animal studies? Thank you.
Yes, absolutely. So our measures work as an order parameter, so they can be used in a wide range of applications, including CT scans, for example, because we can discriminate between randomness and structure. So you can see how useful it is, because if you're looking at an image and you want to discriminate noise, then you have actually not non-random, not uniform distribution from where you can actually discriminate between what might be structure part of the image and what is not.
Okay. Right, lovely, thank you. We're just right on time. I would like to take this opportunity. Thank you, Dr. Zanil, very much for your presentation, and also thank the attendees of today's scientific session. This has been a very informative session. Any questions that we were unable to answer today due to time constraints will be passed on to the speaker, who will then try to contact you later with an answer. Thank you.
Thank you very much.